Okay, so picking off from the previous week where we discussed minerals and qualities of minerals, so this week we are going over igneous rocks specifically, and we'll briefly go over some volcanic hazards that are involved with igneous rocks. First and foremost, what is an igneous rocks? It's one of the three most basic types of rocks. So we have igneous, we have sedimentary, and we have metamorphic rocks. So we'll cover the other two in the following weeks. Igneous rocks is formed with molten rock or melted rock, and this is in the form of magma or lava. So the distinction between the two is that lava is when that molten material has now breached the surface and it's at the surface level. Magma is when it is still underground. So an igneous rock has interlocked crystals that form around each other, and each of these crystals are essentially different pieces of minerals that would be interlocking each other. And those are the same minerals that we went over last week in our minerals lab. So lava, once again, is when we have molten material above ground, and the magma is when we have molten material below ground. And when this cools, we form igneous rocks, and we have an example here of obsidian, which is a volcanic glass. And depending on where that molten rock is, when it cools, it will determine the size of the crystals or lack of. So here we have obsidian, which is one of the igneous rocks. It's a volcanic rock, or also known as volcanic glass. It looks very glassy in nature. And it has no visible crystals whatsoever. You can't see it. It's completely smooth. It's completely glassy. So the size of the crystals, or lack of, on a igneous rock samples will give us indication in terms of depth of where that molten material, lava or magma, where that cooled. So as we approach the surface, we have less and less crystals versus if we are deeper down in the earth. So, for example, if we have a very spongy material that's very vesicular, this is also created very close to the surface where we have a lot of escaping gases. And before those bubbles can essentially pop and that molten material settle back down into a solid mass, the material will cool and freeze that bubble structure. That's what we see here. Or if we have our molten material that cools relatively deep in the earth, it gives the hot magma time to form crystals, or for those individual crystal structures to grow. So an example here is where we have granite. We see these pinkish feldspar crystals, the black micas, the kind of grayish opaque quartz. Those are fairly large crystals. We can see them. They look fairly coarse. And those crystals took time to form. So that molten material stayed molten and cooled very slow. So that rock stayed hot for a very long time. Gave the crystals a very reasonable amount of time to grow into what we see here. So we use igneous rocks in various forms in our day-to-day life. Primarily they're used a lot for aesthetic purposes. So we have granite countertops, which has been a popular trend in the last several decades. We have pumice that is currently being used as an abrasive type of material. Commonly this is found in soaps. If anyone does any type of mechanical work, there's stuff called lava soap or pumice type of soap to help clean very gritty or dirty hands. Pumice can also be used in beauty products as an abrasive when we're dealing with skin. Of course, Mount Rushmore is a large igneous body that was carved to represent the president's head, and the materials used in asphalt roads are mined out of igneous materials. So how is igneous rocks, or the different types of rocks, created? So they're categorized based on the different types of minerals that are present um, and where they cool, and we get different minerals at different depths. So what we have here is the Bowens reaction series, and we have different types of igneous rock types. If we see on the far right, we have ultramafic, mafic, intermediate, and felsic. So a good way to remember this is to think dark to light. So ultramafic and mafic are going to be the very dark igneous rocks. They're going to have a lot of dark minerals within it. And the felsic is where we have a lot of light minerals, and the intermediate, of course, is somewhere in the middle. And these occur at different temperatures, as we can see on the far left, where we have ultramafics forming at higher temperatures, and the lower temperatures is where we get the more felsic type of rocks. So the Bowens reactant series is where it gets split into two different branches. One's called a discontinuous series of crystallization, and the other is called the continuous series. So it's discontinuous because there's breaks in between these arrows of where these specific minerals will form, where we get olivine that will occur within a set range of temperature, pyroxene, amphibolites, biotite micas, etc. Versus the right side, where we have a plagioclase feldspar, where we get more calcium-rich, more sodium-rich crystallization of this particular feldspar based on our temperature, and that drives us from a more mafic type of material, so a darker material, towards a more lighter material. So in our composition, we talked about ultramafics, which is a very dark type of material. This is where we end up with a lot of dark greens to black, a lot of olivines, some pyroxenes. That's where we're seeing a lot of these. Mafics, green to dark gray, pyroxenes are most abundant, followed by plagioclase. So a lot of dark minerals. Some intermediate. So this is something in the middle where we have black and white. So the plagioclase is most abundant, and we see a lot of amphibolites, amphibals. So this example here is a diorite. You can tell that it's a diorite because the salt and pepper look to it. And then finally we have felsic, which contains a lot of the light-colored minerals. So quartz feldspars are most common. We see. And in our lab, for the igneous labs, we'll be focusing more so on the felsic intermediates and mafic, not so much the ultramafic. But anyway, so for this slide here, we're looking at the texture. So texture in igneous rock is in respect to the grain structure or the size of the grains. So as mentioned earlier, that cooling time affects the grain size. So if we have molten material that stays hotter for longer, it gives the individual minerals and crystals within that molten material time to grow. So these are all would be considered as an intrusive igneous rock. So it occurs, or it cools and is formed inside the earth, so it's intrusive. It's coarse grained, which means it's phaneritic. So phaneritic means it's very large grain, very coarse. Coarse grain would be phaneritic. Pegmatic would be a very coarse grain, and porphyritic would be comprised of phenocryst and matrix. So this would be an excessively large crystal within a crystal of a certain mineral within a body of smaller, very smaller, much smaller material. So takeaway from this would be that intrusive material, intrusive rock, cools slowly. It's coarse grained. It's coarse to very coarse grained, and it cools slowly, and it cools within the earth. So you will see visible grains with the intrusive igneous rock. So for example, here we have very large crystals in a body of very small crystals. So this would more or less be a porphyritic type texture. Right, where we have large phenocrysts inside of this mass, what we see here in the cartoon as ground mass. Right, and an example from a rock slide. And the second texture that we have is extrusive. So the two different textures we have are intrusive. So cools slowly, cools within the earth, stays hotter for longer, has very large grains or coarse grain, and versus the opposite, which would be extrusive. So it cools outside of the earth or very close to the surface. So it loses its heat very fast, so it doesn't give the crystals time to form in this igneous rock. So it's a very fine grain up to the point where it's glassy. It also could be vesicular because as this hot magma material approaches the surface, it starts to degas. And as this degassing happens, it creates a lot of bubbles. Think about like the fizz or the foam when you crack open a shaken can of soda. So there's a lot of degassing occurring. And since this molten material is being spewed out onto the surface of the earth or close to the surface of the earth, the molten material that's surrounding the bubbles that from the degassing freezes, and we end up with this vesicular type of texture on our extrusive igneous rock. So extrusive igneous rocks will cool very closely to the surface. It cools quickly, so it doesn't allow time for any type of crystal growth. So it's fine grain or aphanitic. It could potentially be glassy in texture or in look and feel. Or it could also be very vesicular, which is full of hose, so it's very Swiss cheese-like. It looks like a sponge type of material. There's also a chance that it could be porphyritic. So it's porphyritic, meaning it has large crystals in it. And this is usually when the magma or lava carries with it already preformed large crystals with it. So it could be glassy in texture. So we have here an example of obsidian volcanic glass. It can be vesicular or full of holes. So it looks like a bit of scoria.